that should of course not really go down. And you have ultimately a point E again down here somewhere. And it goes like that. So this is a force extension graph, right? Like we already started to see in this one. Sorry, in this one here, same thing, but just a closed loop, if you want to say so. So what is now the limit? Which point now, A, B, C, D, E, is the limit of the proportionality?
B.
Yeah, B, okay. And which point shows the elastic limit?
It's also B.
Okay, interesting point. It's C because it's still showing elasticity. And it would actually go back, which we can't see here, right? Because it continues further. So what it means is elasticity goes up to here. Yes, it behaves a bit different, but then it's still proportional, but in a different angle. So it can go back. However, in this way, here we see clearly there's a difference, right? So that's what we meant before. When we overstretch, then we have an extension which we cannot go back to zero anymore. That's basically this one we talked about before. Huh? Okay. And then the one I wanted to see, look at here is, what can you say about this A and B spring? What is the difference in these two setups of the experiment?
It takes more load to gain the same amount of distance. I think it takes double the amount of load to have the same amount of extension on B.
Okay.
And
Yeah.
for A, it's half the amount of load that can get the same amount of extension.
Yeah, okay, good one, right? So we see that relationship we know from the table. Yes, accordingly, we basically kind of double the spring constant, right? With the parallel setup here. So it's like 2 in 1. So it's like from the outset, you could as well say this is like one spring, but with the double K. And henceforth, of course, we need different force, whereas this one is a very different setup, like you just said, accordingly. Huh? Okay, yeah, that's good. And then I would like to go into this one and say, we have a couple of questions to this one. First, which has the greatest value of the force applied?
C.
When you look at the behavior of C, what is C, the curve? Is it linear or non-linear?
No.
Right, so basically that's already something special, right? Because we only can calculate for the time being, or within our curriculum, springs which follow Hooke's law, right? So Hooke's law means very clear. It can only be linear. So any non-linear behavior is something we cannot calculate. So we exclude it and say, okay, it doesn't obey Hooke's law, hence it doesn't follow it. And that's why then the question stops anyway, because it would need differential equation stuff like that. Okay, so when you go back again to say, okay, basically, well, theoretically, A, right, still there, only at the very end it has some stretch out. But obviously, A, B, D follow Hooke's law, at least A up to some point. Now, which has the greatest value of the force constant? Which is K, right? The spring constant. They use it, they call it here in the context force constant. We would call it spring constant, actually. So, spring constant.
D.
Or yeah, exactly. And why?
Because it takes a higher amount of force to make a small amount of extension.
Yeah, exactly right. So there's like a blockage from the K. Of course, nothing works like a multiplier here. The K is always kind of a blockage, so hindering the force to fully make the extension. And that is exactly what happens here. So which one is obviously, to phrase it a bit differently, the least stiff material or the least stiff spring? This is a bit a tricky question, actually. This is a bit.
Sorry, I didn't hear. Hello?
So which one is the least? Yeah, do you still hear me, Chris?
Yeah.
Hello.
Yeah.
Okay. So which one is the least stiff spring? Just to phrase it a bit differently.
A.
When you look at the graphs. Yeah, A, exactly right. So in such a situation, let's not, how to say, let's disregard that part, because this is, and say, well, it follows hook law up to here. So henceforth, I can compare this one to this one to this one, and that's just another expression. So when we say the most stiff, this is the one which the highest resistance, kind of. Again, we are kind of in a resistance, or the spring factor, the spring constant, whereas here it's obviously comparatively weak, so it can be quite easily stretched with a little bit of force. It goes quite a way, up to the point where it, of course, behaves non-linear. Okay, and well, obviously very clear which one doesn't obey Hooke's law.
C and A.
C, yeah. When you say A, then I would just say from a certain point onwards, huh? Because up to here it follows Hooke's law. So then, and it's good that you say A, because we never know how the question is meant. Sometimes it's really only, okay, this is the spring, because it's all the way not obeying Hooke's law. This one is mostly, but not at the very end, which actually, if you would further stretch it, may happen here and here as well. It's just not yet gone there, so to speak. Maybe it only starts up here, right? Same for this one, maybe only up here. But sooner or later, it will happen to all of them that they do not follow. But then we know what happened, because it's not elastic anymore. It doesn't go back to the origin. It will remain in a certain extension. Huh? Okay, I think that's very clear. So we can move on. That's just to keep in mind for the calculations. Now we go into the next one, for stretching material. And this one is a bit more different. Of course, it starts with the same basic outset, but nevertheless, it is a bit different, because this is now not a spring. Huh? So when we talk about spring, we talk about extension, not really stretching. But stretching means really like what we had before, the forces to put it under tension. And this is like of how we can stretch the wire, for example. And the word we are using in that context is strain. Huh? So instead of extension, we call that strain. And strain is the extension over, of course, over the extension over the original length. Quite straightforward, actually. Just the word itself may be a bit. So strain is in this sense not a force. Sometimes the system is under strain. That's happening as well as an expression, or a person feels quite some strain as well. Then we, of course, are tempted to think it's a force, a pressure, something like that. But it's in the physical content, it's meaning it's the extension over the original length. So extension, of course, we still call it x, nevertheless. And typically the original length is usually capital L. And we call that epsilon quite often as well. So it comes with the Greek. That's this one. Just another symbol, actually. The content is really straightforward. And we can just frame it actually as well. As we say, this is what we are talking about. That would be the strain. Huh? Okay. Now, what we can as well say, of course, one is now the behavior of the material, and like what percentage, for example. We could express that even as a percentage, right? Not just as a fraction. If we do it by 100, but typically we have it as a factor, obviously. We could as well say, of course, looking now into the forces. Huh? That's the difference. So the forces we call stress. So we have to be like weight and mass from everyday language. We always talk about weight, but in reality we talk about mass. But in physics, of course, we know mass is mass and weight is weight. One is, well, mass and the other one is a force. And here as well, in everyday language, strain and stress and pressure and tension, that's all put into the same bag. And people usually mean just, well, something is under force, under the influence of a force, either squeezing it or pulling it, including persons as well. We know that, right? People are stressed out. So here it may clear, but they may say as well, under a lot of strain. Physics is different. Strain means the centimeters, so to speak, and stress means the relationship of the force. So the normal force, and always to keep in mind, we talk about the normal force. So even if that's a material and for whatever reason the force is pulling it like that, old story applies, so to speak. We only look at the normal. Very important. So we see that all the time. Like we have to bring it into our XY system actually, and when it's normal to the surface or the cross section in that context, then of course this is the one we are interested in, because only that one creates the stress, which makes a lot of sense, because this one, we saw that from before, very beginning. That's why it was on one side simple. So the tensile forces, the compressive forces, they are act normal to the cross section. Now that's important to keep in mind. However, if we have something like this one, then of course it goes just in a different direction. That's the point, right? So in this context, of course, we could have compression and tensile forces as well, but of course then they may go like this or they may go like that. There are still compression forces or tensile forces, but of course obviously just in the y direction. And of course if we have a force which is going something like this, and this one like that, then of course it obviously is a vector, and the vector is split, so part of it pulls in this direction and part of this pulls in that direction. Same thing here. There goes the vector in this one, in that one. So what we, as a result, have them, this one would now expand, right, in both directions. On one side, it would become a bit longer because we have tensile forces acting in this direction, not compression. And in this, but we have it in the y direction as well, so it gets a bit widened. So the question is then, what is the angle of the force, and hence which part is how strong, that we can see how much is this one widening, because that's what it does, and how much does it elongate, right? How much does it make longer? Just to keep that in mind. Typically, we would not have such calculation, but to keep in mind, we always split it into x and y direction, and that's why here stress. So it's the normal force. Would be the same if, of course, we would have a force which is on this direction. Then it's just that is the normal to the one, and that one would count because of our Cartesian coordinate system. So we take the normal force to the cross-sectional area. And you see, this is something like pressure, but the other way around, in that regards, when we are pulling. So if we talk about pressure, same thing, normal force to the cross section, but it goes inward. or it's inside the box and presses to the outside. Then we rather call that then the pressure and not the stress. Because we can see from the measurement, of course, it's of course Newton per square meter, right? So it's exactly like pressure, which we of course call bar or Pascal. And that's why in a next section, so we can say this one has a specific symbol. To make life a bit complicated, it's E for the Young modulus. I don't know, so it's called the Young modulus. It's a property of material, of how much stress it can resist. For example, if you think about the building, maybe a bridge out of steel, then it's very important that we know, because let's say maybe it's a bridge, something, well, let's say the very famous Golden Gate Bridge in San Francisco, like hanging, right? So here and here, and then we have, well, something like that, huh? So it becomes very important that whatever is happening here, even if it's wires, they are made of many steel parts, or theoretically they could be like that, with steel bars being hung in order to keep it straight here. Then it's very important that we have the very proper material which can hold that load, both static first, so that we can say, well, there can be, let's say, 1,000 vehicles at the same time on it, but on the other hand, they drive. And these vehicles induce so-called dynamic forces. Because they drive, that creates frequencies, amplitudes, additional forces. So that's why then it's very important to dimension it properly. So the engineer in charge, or the engineering team in charge, needs to select the proper material that they can say, this is the steel we need with the specific Young modulus in order to keep the certain stress over strain. That's what it is. So we make a relationship between stress over strain, and we call that the Young modulus, which is very practical. It seems at first a bit like what? But in reality, of course, it's stress over strain. So the normal, the Newton per square meter over our length, which is nothing else but, of course, a fraction, right? We have extension over original length. Here is without a dimension. It's just, and as we divide it, so if, for example, the extension over the original length, then it's like 10%, but that means 0.1, because we are measuring the extension and not the new length. So it's a 0.1. And if you look at the stress divided by 0.1, then it's like a multiplier, right? And it's like factor 10. So the Young modulus will become greater. If it's 20, it becomes even greater. If it's 30, even more, right? So it's like an amplifier because it's underneath here. It's divided by, and the extension is a fraction of the original length under normal circumstances. And what I have not mentioned yet is this one, the stress, just coming back to this one. So we can as well, of course, write force over area. That's nothing new. And it has a symbol. And this is sigma. So this is sigma. So we have two important terms we really have to keep in mind, not to mix them up. They're on their own very straightforward, actually, very practical. Stress, yeah, the normal of the force to the cross section of the area, but it's called sigma as well with the symbol. Stress, you can imagine S, sigma, that's where it comes from, actually. Greek letter again. And the strain, that's a bit less obvious. That's the epsilon, which is nothing else but the ratio of extension over the original length. So here we have like the opposite of pressure, if you want to say so, because we talk about extension. So it's Newton per square meter. And then the Young modulus puts these two into relationship to each other. So if stress is sigma and strain is epsilon, so obviously that's what we get. And because there's no change, And that, of course, is Pascal, Newton per square meter. So you see, it's like pressure, but the other way around, meaning extending it instead of squeezing it. But of course, if you're inside the box and the pressure is pushing it out, so from that perspective, you have then actually stress in the wall in order to extend it. Depends on which viewpoint you apply. And because, of course, strain has no dimension, Hainsworth, the Young modulus has, of course, the same dimension as the stress. So it's, of course, still in a Newton per square meter or in Pascal. Is that okay, Chris?
Yeah.
So it's a lot of definitions, right? And when we can, of course, look at, we can always link it with our fabulous graphs. Of course, it's just a matter of what we plot on X and Y. So in this case, I can make strain over stress, or stress over strain, actually. Sorry. And of course, surprise, surprise, there's a certain behavior very similar to Hooke's law. I'll make it a bit less. So, okay. And the gradient, well, if you look at it, the gradient here and here, that is obviously stress over, also the gradient again, of course. And what is the gradient therefore, Chris? Just what you see here, nothing else. There's nothing hidden. How do you define the gradient in this case? How do you? Yeah, please go on.
I forgot the stress over strain.
Yeah, exactly. Just straightforward, right? Just normal. It's always y, also delta y over delta x, right? So no matter what, that's the beauty of it. So it's, of course, stress, over strain. Stress over strain. And what in terms of symbols? So stress is sigma. So sigma over epsilon. And what is sigma over epsilon when you go back? When you look at what we did here, let's make it like this. So what is the gradient actually? How, like we had it for Hooke's law, right? We could call the gradient the spring constant. So what could we call the constant here, that gradient? When you look at the relationship, when we put it into the stress over strain, sigma over epsilon, what is that, Chris? The one, we know it. When you look at the notes here.
Young modulus?
Yeah, exactly. So that's the point. Yeah, exactly. So we have the same relationship. It's just a matter of how we put it together. So this is our gradient, and this is like that. In that sense, straightforward. So that Young modulus is nothing else but the gradient of under which stress we get how much strain. Same thing as before. So we had the extension as well in our gradient chart here with Hooke's law, but this was an absolute extension. That's the difference. So we have an absolute extension in the Hooke's law. How many centimeters has the spring expanded? Whereas when we talk about the stretching material situation, also beyond the spring, of course we want to apply the same logic. There's some tiny modification, and that one is that we talk about the strain, which is nothing else but a ratio. The extension, here in Hooke's law we only use the extension. In the stretching we use strain as a ratio between the extension over the original length. Has its reasons why we make it like that, because it becomes very practical with the young modulus. Why we don't take the extension. So this is normalizing it, right? The moment you put something changed, also the change, the delta, in ratio to the original, of course, you get a factor. And that means you normalize it. So it doesn't matter if you had an extension of 5 centimeter, 50, 500 or whatever, you always put it in ratio to the original length. And that makes it, of course, universally applicable. And that helps to define then a young modulus, which is normalized for any material, basically, and say, well, and you know exactly the parameter or the value of it. And you can say, well, this is actually a more flexible material or not. Or in other words, how much stress do you apply? Like what we looked at before, there's no difference really to the Hooke's law in its logic. Right? Is it steep like that or is it flat like that? So in this one, of course, a lot of stress needed to get a little bit of strain. Makes a lot of sense. This is ultimately force, but again, the force in ratio to the area. And the normal force to be then very precise to the cross-sectional area. But in its core thinking, it's the same thing. There's a force involved and there's an extension involved. So Hooke's law and Young modulus, they're basically the same. Hooke's law is for springs. Young modulus is for non-spring material, so meaning any other, which is not in the form of a spring. And the gradient is this case called then the Young modulus, obviously. And in order to make it easier applicable for practical purposes, we put the force not as an absolute force, but in ratio to the diameter. And even more so here with the strain, we do not take the absolute extension. We put that as a proportion to the original length. So henceforth, these are extremely close related. And to give it a bit of practical sense here, so we see how these young modulus are for various materials. And as we said, the young modulus is in Pascal. So when you see the G, what does the G tell you here in that G Pascal?
Giga is billion.
Okay, yeah, giga, that's a good one. That's where it started, exactly. So it's like always, like gigabytes, same thing. Gigapascal, giganewton, gigawatt. So it's obviously a pretty huge measurement, actually, when you think of it. Not mega, not kilo, right? Like we quite often, kilo is something we are quite often encountering. Mega a bit less, maybe in power production. But giga is really large, like you just said it, yeah. Kilo, giga, kilo, mega, giga, so 10 to the 369. And you look at a bit at the values, right? So you can see here, like steel or iron. This is like we expected, quite high, of course. So you need to apply. So it is a steep gradient, so to speak. Henceforth, of course, you need to apply quite some force until it starts to move. Whereas, which one is the lowest? Which one doesn't hold a lot of stress?
Rubber.
Oh, not necessarily rubber, for example. Okay, this is not unexpected, right? I mean, rubber, of course, the moment you apply a bit of force, of course, it starts to extend like wild. That's, on the other hand, what you exactly want with rubber, right? And from what is maybe surprising, with, say, brick, right, for example, or concrete, they can't hold a lot of, the young modulus is pretty low. And this is exactly the reason why we usually have, we use a lot of concrete, right, to make buildings or bridges or whatever in the end. And if you remember, or maybe you don't or don't know, that's okay. You are never just using concrete. When they are pouring concrete, it will harden and then it keeps the form like in a mold, of course. So you more or less can shape it in any way you want. Let's just say a pillar, for example, to hold several pillars to hold ceiling, which is then the floor for the next level. Would you say this is a very good idea just to use concrete alone, or would you maybe use some additional material?
So if we use concrete alone, then if tension is applied, then it will break.
Yeah, absolutely. Very good, Chris. That's exactly the reason why meaning in construction is used what it's called reinforced concrete, right? So first you always see the steel bars being like three-dimensional models, maybe like that. Depends a bit how they do it. So a couple of them like this, and in the end, then there's the wooden frame around it, and then is the concrete coming in, right? Something like that, and filled it up and compact it. The point is exactly that it will be a very good combination in order to resist tension and pressure. So concrete is very good for pressure, for example, from the side, like that, but of course very lousy if it comes to pull. Whereas the steel bars inside, they can absorb that. So we have the good combination of these different two forces to withhold. And that's why, unfortunately, when you have an earthquake, where you have exactly various forces, they pull and push, and buildings with a good reinforcement will stand, those with a weak reinforcement will crumble. And you unfortunately see that in many cases in the world, when there's a strong earthquake, quite often buildings collapse, but not all. And those which collapse are those with the very weak or if even hardly existing reinforcement, maybe much too thin. Maybe what is in China, there's a saying, the bamboo reinforcement means very thin. And that, of course, cannot withhold the force. You can imagine the modulus here if you look into the steel. And of course, you need to have a certain diameter then in order to make it resisting a certain force. So when we talk about steel here, this is just Newton per square meter. So if you have very thin steel, then of course you can't withhold so much force because obviously the cross section, the square meter, is only very low. Hence, the force to be applied cannot be too high. But if it's thick, say 2 fingers thick, 3 fingers thick, so to speak, it can of course absorb much higher forces. And that's why, in order to have buildings earthquake proof, there's certain minimum requirements of the thickness of the steel to be used. Plus, of course, the concrete then for the pillars as well, of what the diameter of the pillar should be, stuff like that. So if contractors, builders do not follow those principles, or actually more than guidelines, they're usually even by law, and they violate that, then unfortunately, then there's a disaster and people, well, get killed, like we see, unfortunately, in these earthquakes. So there's a very practical application with these young modulus in order to dimension our construction, our machine, our whatever properly in order to withstand certain forces. So you cannot have a truck be loaded with 10 tons if you don't dimension it properly. Seems very obvious, right? So if you load it with, if you dimension it wrongly and you want to load it with 10 tons, it will obviously collapse. That's exactly what happens then with buildings. So this is actually the practical usage of that young modulus. Okay. Now, when we look at these two materials, what is the young modulus for A and B? How would we calculate it for B? Make it a bit larger.
Strain over stress.
Okay, yep. Just a second. So just to, is it really like that? Let me just go back quickly.
Oh.
Just to keep in mind, huh? Exactly. Yep. You want to have the stress over the strain. Of course, you can always invert it. You can always say E minus to the power of -1, but that's okay. So, and of course, the chart here is already giving us the idea. If it would be very nasty, it could be that it's actually strain over stress, so that it's reverted in the chart, right? Oops. So that it says strain over stress in the graph. But that is usually not the case. So that any case questions tries to mislead you by having strain here and stress on this one. That's no. Okay. So now what is it for B?
I think it's 14.
Okay. When you look at it, that is a fiver, right? So it must be a bit below half in tendency. It's
12?
always a bit tricky with these. Yeah, 12. It's always a bit tricky with these boxes, right? What is what? But obviously, we have 10, I guess. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so it helps to count. So that means you have 0.5 per increments. So it's 1, 2, 1, 1, 1, 2, 3, 4. 1, 2, 3, 4. Okay, so 12. Okay. For B, sigma over epsilon is 12. And then not to forget the 10 to the power of 6, just in case. And what is our strain? That is a bit tricky. In a tiny little bit, where they try to catch us. Otherwise, it would be too easy. So first the value, Chris. What value do you see? What do we see? So if we go down, we end up here.
0.24.
Okay, so we have 0.24. Now I write it on the side for some reason. So we have 0.24 what? When you look at the unit of measurement, percentage. Huh? And what is the definition of epsilon for the strain? Is that measured in percentage or fraction?
Fraction.
Or fraction or proportion? Okay. So what is it there for? What do I have to write down henceforth for the epsilon?
0.0024.
0024. Yeah, exactly. Yeah. Yep. So this is a little bit a tricky part that they release the strain in percentage, right? And the values are already small. So when we do not pay too much attention to this one, then okay, 0.2, okay, it stretches by 24. In that regards, if it would be without the percentage, it would already stretch 24%. Huh? That's what the 0.24 would mean. But it's 0.24%, so it only stretches with a tiny little fraction under that pressure of 12 10 to the power of 10 to the power of 6 Pascal, or megapascal, in other words. And the result is how much? What do we get as a value?
Wait, I got 5.E9 because I'm using my phone
Yeah.
calculator.
Yeah. So, okay, so that means 10 to the power of 9, huh? Okay. Pascal, okay, because we still talk about Pascal for the E modulus, so E. And what could we then, in simple words, so to speak, what would that be? 5? How many Pascal, K, W, G?
G.
G, huh? So there we would have 5 gigapascal, huh? 10 to the power of 9. And when we go back to the list here, it's gigapascals, and it's only 5. So that seems to be, well, it's not really anything close. That perspex, whatever that is, something more rubbery, obviously, probably along the lines. Polystyrene, yeah, there we see it. So like one of those cups, or the food containers, unfortunately, still quite in a few cases. So something very weak. So you see the E modulus actually, it stretches 0.24% under the influence of what seems to be quite a force, actually, 12 times 10 to the power of 6. But that results in an E modulus of 5, and that seems to be very weak. So it already quite some force which is applied, but yeah, it's a polystyrene cup, so that we know we can easily squeeze that. Okay, what about A? What is the easiest point to calculate the Young modulus?
The point where it just reaches the when it just
This
plateaus.
point, yeah, right. So where it becomes inflexible, actually, right? I mean, of course, you could take it here as well, right? Because it's linear, so you can take any, right? Any of whatever you want. Just make sure when you pull down that you have the right delta, so to speak. But of course, this is the easiest one because this is just the max, and well, surprise, it's easy to read because this is what we are talking about, right?
Yeah.
So what would be the values, Hansworth?
15 times 10 to the power 6 over 0.001.
Yup, 0.001. Exactly. And that is how much? Or how many pascals?
One times, 1.5 times 10 to the power of 10.
Okay. And how would you simplify that to bring it into, let's say, obviously giga, right? Because that 10 to the power of 9 is the closest. So
15 G Pascal.
yeah, exactly right. So just go up. It's very simple, right? But you need to know how. Otherwise, it's obviously not simple, exactly. And so that's one way to express it a bit easier, that you don't have to say, well, 1.5 times 10 to the power of 10 Pascal. If you are really doing an experiment or something like that, or you dimension it in the engineering office, you would never talk like that, right? You would talk about 15 gigapascal or 5 gigs Pascal, or maybe not even say Pascal, because everybody knows you talk about Pascal anyway. Okay, yeah. So that's a nice side effect of keeping such numbers straight. And okay, then a couple of questions. Let me see. I don't want to do all of them. Maybe we do this one, 16, and then I can still give you the 17 and 18, talk a bit about 19. Yeah, there's still a lot of coverage. So let's just do 16 because it has a bit more in it than just what we did. One is, of course, to have the graphs. Okay, understood. Clearly, I see that. Now it's just some calculation in order to do that. this is very typical, right? You get a lot of information, and now we have to calculate. Actually, the question is calculate the Young modulus, and in order to do so, you have to, of course, calculate stress and strain. Otherwise, we couldn't do it. So, in a typical question, you would not get calculate the stress and strain. They would just say calculate. Oops, that's too much. Say calculate the Young modulus, right? That would be a very typical question. So then what do we do, Chris?
The stress first.
Okay.
Stress is so I want to convert it to I think I have to convert it to meter squared.
Okay. Yep. Huh? That's basically the key tricky part here. Yep. So when we stress, so when I write down my stress, my sigma, what is the, just to briefly, it's always good to write it down because in case something goes wrong with the numbers, you at least get the marks for having properly identified the formula. So what is sigma, Chris? Or the formula?
The force, it's the force over the area.
Okay, yeah, exactly right. Like pressure, stress, pressure, same thing. Also, in that regards. Okay, all right. So force we have, right? So we have 50, obviously. Newton as it should be. And what about 50 square millimeters? Oh, 0.5 actually. Not even 50 square, just 0.5 square millimeters. What is that?
Uh, 5 times 10 to the power negative 10.
That's a. I know what you do. In such a case, first of all, I would leave the 0.5. I would not change that because 0.5 is 0.5. So no need to make it more complicated. And then what is millimeter in regards to meters?
1,000 to 1.
Yeah, 1,000, huh? Or in other words, 10 to the power of 3, or as we talk about, minus 3, huh? In this regard. So if I do 10 to the power of 3 times 10 to, also minus 3, 10 to the power, because it's square millimeters, right? So that is my result. So what is then the result of my square millimeters expressed in meters? When you look at this one.
That's
what is 10 to the power?
Yeah, meter squared.
Yeah, but that's meter square. And what is the value here? What is that?
Negative 10 to the power negative 6.
Exactly. Huh? All right. That's the point. If you are in difficulties to do something like that, then just go take the value because that's the value. It remains, no change. However, the unit of the powers are just, okay, millimeters 10 to the power of 3, also minus 3, because I'll go now from millimeters to meters. And once more, because it's square. So, yes, that would be, then you, in order to be on the safe side. Huh? Exactly. Newton per square meters now. Okay, and what would that be when we calculate it? Or if you would have no calculator, Chris, what would you get? If you would have no...
I first turn it to 5 times 10 to the power negative 7.
Okay.
And then I do 5 over 5 times 10 times 10 to the power of 7.
Okay, close. Yep. Just there's one with what you just said with the 7. Is it going in which direction does it go? So when you say, because I mean you were right, but then you have 50. There's not 50 divided by 5, and sorry, 5 divided by 5. It's 50 divided by 5.
Yeah, so the times extra 10.
Okay.
So it's 1 times 10 to the power of 8.
Yeah, exactly. Okay. One. So that's what I mean, right? Of course, in the test, you would just punch it in most likely as long as you can utilize it. But with such comparatively simple numbers, it's a good mental exercise to put that a bit into perspective. Obviously, clearly, the 10 to the minus 6, right, is actually the same as 10 to the power of 6 when I write it above, because it's divided by. Make sure it's clear here. So then I can as well say 50 times 10 to the power of 6 divided by 0.5 is 100, and take 2 away. So, or add 2 then to the tower height. Huh? Okay, one, and that is in what measurement now? As a unit of measurement, I mean.
Pascal.
Yeah, exactly. Yeah, because you rightfully turned it into square meters. Huh? Otherwise, you would not get. All right, that was sigma. What about epsilon now? I just put it here. We still have space. That's what is the strain?
The extension over the total length.
And which total length? Which total length? Because you have 2 values.
The original length.
Yeah, exactly. Yep. I mean, I'm sure you had that in your mind anyway, but just to make it very sure. Okay, so the extension is how much?
0.1 cm.
Okay, and the original length?
200.
200, exactly. And we have cm over cm, so it doesn't matter. I don't have to convert it into meters because it's a ratio thing. As long as they are both in the same dimension, it's okay. A unit of measurement, I mean. So what is the result of that?
1/2. 0.0005.
Okay. Okay. Or we could as well, or if you would have to do it in the power of 10. Did you say 0, 0 or 3, 0? Sorry, Chris.
0.0005.
Exactly right. Okay. Yep. Thanks. Oh, how could you write that a bit more, say, conveniently?
5 times 10 to the power of -4.
Yeah, exactly right. Because obviously we're gonna make some division, right? Here, so we have 10 to the power of 8, and we have 10 here as well. So it makes life a bit easier. I mean, again, if you would have no calculator, for example, this one makes it very complicated, but this one makes it rather easy, actually. All right. Now, the final calculation is now again, as we say, sigma over epsilon. So 1 times 10 to the power of 8 divided by 5 times 10 to the minus 4. Huh? And what do we get there for the Young modulus?
First, 1 over 5 times 10 to the power of 12.
Okay.
0.2, it's just 2 times 10 to the power of 11.
Okay, yeah, very good. Exactly. So that's what I would do, right? Avoid the 0 point. Just get a number. I mean, in this case, very clear, just an integer, and then just adjust the power of 10 accordingly. Huh? Okay. So, and that is Pascal. Just to write it down. So, if we would go into gigapascal, just to say how many gigapascals would that be? I mean, it's not being asked here, but just as
200.
Okay, all right, exactly. Yeah. Because this makes it easy. As we see here, a piece of steel wire, so we get 200 gigapascal, and we have this comparison table, so we can see and say, is it in line? Okay, it seems to be a bit on the lower side with 200. Iron is 200, at least it's wrought iron. Standard iron would never be as high. That is already twisted, if you want to say so. That gives it additional strength. Some of the material squeezes into each other, so to speak. So this is not really the steel intensity we would like to have. So it's like wrought iron. And that's, if we talk about steel, then 200 is a bit on the low side. Huh? Of course, there's nothing asked here. It just said it's steel, the Young modulus of that steel, but it's not really it's borderline in terms of what material it is. Huh? Okay, so there may be such a table that you have it for comparison and say, okay, judge if that material is suitable, what do you comment, right? Something like that. Then you can say, well, I see from this table, standard steel is about 210, so 200 is on the low side, and I see as well that wrought iron is 200, so this is more like raw, even if we call it steel, it's more like wrought iron, so that's not what we really want. So we should have a different material with a better Young modulus. Huh? Okay, so this one we leave out, this one as well, because we have done now enough of these Young modulus. So maybe just nevertheless, for today, still go a bit into the elastic potential energy. What do you think, Chris, is that elastic potential energy?
So it's the potential energy stored in like when an object is like stretched.
Yeah, all right, exactly right. So basically, I put it in, so to speak, or it holds, right? And as we have done so many of these charts today, let's close today with another chart, very similar, but it goes now one step further, so to speak. We still have the force. We go back to extension, just simple extension, not in ratio to something. And if we now again apply, of course, the linear behavior, something like this, then of course, if we say this is the force applied and this is the extension created, then what we have underneath here, that area, that is actually the work done. Huh? And work, of course, is energy, meaning exactly what we talk about, work done, the potential elastic energy. So this is like nothing new, actually, only the content is a bit different. So here, to make it very clear, we call it extension. But of course, if you think, excuse me, would you, in another context, what could be work? I mean, it's area, right? Work done. What else comes to mind, Chris, when you look at that chart? What would you replace extension with? What would then on the x-axis stand in order to still get work done?
Distance.
Exactly. Yeah, very good. Exactly. So we could as well apply that to distance. Distance d, for example. So, and we know that already, right? Force along the distance, as long as it's in the direction from a vector force point of view of the distance, then of course you get work done. So same thing, nothing different really, because it's exactly the distance the force has to travel, if you want to say so. And that, of course, is then equivalent to the work done. In that specific content, then we call that the potential energy or the elastic potential energy, which is there, has been created or being transformed. Okay. And now, of course, in order to calculate it, so we say, well, what I just said. So the elastic potential energy is work done. Work done, which means when you look at it, what would be an easy way to calculate that now? When you look at the chart,
Divide the force by 2.
Okay, yeah. So, or you can say just half, right? Force times extension. Also, that is now the unfortunate force times x times x, huh? Because it's like a square, right? Like what we calculate this one, and then we cut it in half. Exactly. So the half is more from halving it, less half of the force actually, which of course in reality will be. So if I calculate this one, of course, then this content here is exactly the same as that of the triangle. Or that's why we exactly calculated area of a triangle. Same thing. Huh? Okay, so you see the link between the various parts of what is going on in geometry, algebra, and what is going on in physics. And we call that, of course, like E again, of course, elastic potential energy. And to be more precise, we should use it. That's where E pot and E can. Okay, so crystal clear. And when we now link it, that's the last part we do today. So if we now have this elastic potential energy, of course, we can actually link it to what we know from Hooke's law, right? So remember what Hooke's law said for the force, Chris?
The force in the extension is proportional.
Okay, and equal, when it's equal? What do I have to, what? Yeah, okay, exactly. Huh? Okay, so now it's more math than physics. So we have our F, So in consequence, I can say my E pot, of course, is half kx times x, which of course is half kx squared. Huh? So there's another way to write it. So my potential elastic energy, or my elastic potential energy, is actually go back to Hooke's law, but it's then the square, so half squared extension, half. of course, in the inclusion of the K, also the spring constant. Huh? So that is actually, can see very simple, but what we can see is then on the other hand, the behavior of the potential energy is not linear, right? It's squared. So it's already by the power of 2. So in relationship to the extension. That's quite interesting when we link it with the constant and say, well, K is the gradient actually between force and extension. And the area, we can as well say the potential energy is related to the square of that extension. Hmm? Okay. So either way, so clearly you can see either you are being informed about the force which was applied, then you can calculate, that is very typical, involving a force in order to get the work done, meaning the energy. Or we go a bit a different way and talk about the, say, parameter of the material, which is, say, the spring constant in that case, and say, okay, what is now the potential energy contained there by looking at that spring constant? Then we nearly do the same calculation, right? Still this one. Sorry, K, of course, is just K instead of F, but they have to square it then, or second time X. So that's how these questions go. And we have a simple example here. So we have this one. Let's just look at that one. A simplified force extension graph for a piece of metal. The metal is stretched to its limit of its proportionality, that famous point A. So it has a very practical, and then the total work. Now we see the link to how the metal can break eventually, right? So what is the elastic potential energy? Step 1.
1/2 times 20 times 5 times 10 to the power of -3.
Okay, yep, straightforward, right? Very straightforward. So that we can say it's the force, and hence I just put it really down. So what we get the value of 0.05. Let's leave it like that for the time being. What is the unit of measurement?
Joules.
Joules, yeah. At the moment we talk energy, the moment we talk work, then it's joules, right? Exactly. And what, according to what we are shown, we can assume that it's not explicitly said here, but it's where the graph stops, so to speak. That's where it breaks. It's not explicitly said, but that's what the graph actually tells us. So what is therefore that additional breakage work?
0.05 joules.
That's just the elastic one, because that's what it's, so what we calculated is this one, right? This one. And here it's just still elastic. Huh? So the moment we release the force, it will go back to the original. So of course, if you really extend it, we see here already a tiny little curve. So, but for the sake of the discussion, that's where we leave it. So if you release the force, it will be reversible. Huh? No overstretching. That's why it's purely the elastic energy, actually, the potential elastic energy. But if we now stretch to the limit of its proportionality, so really just up to the top here, so what do we have to include in that one? Because something happens. It's a bit simplified, right? Of course, it's like a jump function. So what do you see happens from here to here, Chris? Because this is a measure point. So it's an infinite small point, as they like to say in physics, or as we like to say in physics. And something happens from A to D, or from B to C. What happens here, Chris?
It instantly like increases in the extension.
Yeah, exactly. I mean, that's highly unlikely, exactly. But in reality, it would go probably something like stopping somewhere here and then go maybe within a very short period of force, would then suddenly stretch like crazy, huh? So to speak. So here it needed like maybe 19 in order to get the 5, but then with one additional Newton, it then whoosh goes from 5 to 30. Huh? So that's why they say simplified version. So it's slightly confusing for the purpose of what we are doing here. So that means if it's going to break, so up to shortly before, it could have gone back to 0, no problem, also extension wise. No zero force, also 0 force, 0 extension. But here it has this kind of jump function. So henceforth, it needed additional energy. And what is the additional energy now beyond the elasticity of what was added to make the metal break? That would be this one, right? So this one, exactly. So we can say this is the addition of the break energy or whatever. So it needs that additional, so you can make a plus sign. And how much is that one, Chris?
1/2 times 20 times 25 times 10 to the power -3.
Okay, yeah. So the additional one, sorry, is
Oh
20.
wait, it's not. There's no like division of 2.
Exactly, because it's just a square.
Yeah.
Or a rectangle. Exactly. That's exactly the point here, which plays a bit around. We are eventually so used to use the half because, of course, that's where we typically talk about the elastic potential energy. But with the break energy, that is irreversible, so there's nothing half. And again, the drawing here is a bit unfortunate. Should have been stopped maybe here at 19, and then from 19 up. But then, of course, you would have had another small triangle included, so that would have made it a bit more complicated to exclude that area again at the end and only have the one which is really underneath, right? But that's why they simplified it. Okay, so 20 times 25, important, yep, that we go from 5 to 30, the delta, which gets sometimes forgotten, not by you, which is great. And then, of course, you have the 10 to the -3. Okay, and that is how much? That would be 50, huh? Also 0 point, I mean, excuse me. 0.5 joule. Would you agree?
Yeah.
Okay, because the reason why we still leave it at 0.5 is because obviously we have to add them up, these two values, so we better keep it with the same. So, and that one in consequence is therefore 0.05 plus 0.5, 0.5 means, of course, 0.55. So calculation-wise, very simple, just to keep in mind, the moment it's beyond the elasticity, you put in additional energy, or energy is needed, either way, and that is then nothing else, of course, than force times distance, if you want to say so. So you have the complete one underneath, like in the normal force distance diagram. This is a bit a special case here. All right, okay. So I'll put these 3 questions, 17, 18, 19, onto the Skype afterwards in a couple of minutes, so you can find it there. And then next time we just go into some question paper, huh?
Yeah.
To still continue with density and pressure, but in a mixed way. So now that we have covered all the subjects, huh? That is what we have covered so far, is all the total material. the content. Now it's about time to do only questions. Huh? All right. Then thank you, Chris, and see you next week. Huh?
Yeah. Wait.
Right?
Yeah.
Mhm.
Yeah.
Right. Yep. We are still on Friday. Then the week after we do Sunday. Huh? But next week we do Friday. All right.
Yeah.
Okay. Thank you.
Thank you. Bye.
Bye.
Wait.
Oh. Hello.
Oh, wait. Oh. Hi, Chris.
I'm winning. No, I think.
Wait.
Come back season.
H. Word with an H.
HIV. AIDS.
HIV.
No.
Hive.
Wait, that's
Hive.
too little.
HIV.
No, but like that's the best
HIV.
one.
HIV.
Stop. You didn't
Start timer. Start timer.
Stop.
Timer.
I
Wait,
just started.
HOOD.
Hood.
HOOD. Hood.
That's too little. That's too little. Oh, I'm ahead of you anyways.
Oh,
I'm still winning though. I'm still winning. Yogurt. I know there's no H. There's no H and T.
Oh yeah.
Trail. Try trail. Troll.
Why are you helping him? Shut up.
Because I'm still winning. you guy. Do it. Wait, who joined?
It's
Who's
Chris.
that?
My friend.
Okay.
Start that timer.
Whatever. This is so good,
Wait,
guys.
why did you still get so much points? He's gonna win again!
We're so.
Oh my gosh. Wait, I don't even care if I'm gonna lose anymore. I wanna see who's gonna win.
God.
I'm not losing this.
Okay, go, Chris.
J.
Fine. No, it doesn't work. Joe.
Simple. I like it.
Joe Mama.
Okay, anyways, let's go. Okay, Joe.
Yay, he got 9 points. I'm still winning.
I'm gonna use my hint, guys.
You cheated.
It's there for a reason.
If she's cheating on a game, imagine in a relationship. If she's cheating on a game,
What
imagine
the
in a
hell?
relationship.
Oh.
Shut up.
Oh, I see one.
Stop.
With the V.
Chris.
I need to win.
Chris, click the start timer.
No. That's too little.
Everyone.
Chris, don't click it. I will kill all of you. I'm gonna kill myself. Stop! I'm trying to find a Wait.
Just do Van.
That's too little. It's too little.
Don't
Wait.
tell her. Don't tell her.
No. Whoa.
Oh, you should have done Woven.
I don't care. I don't care. I'm still winning this. I'm still winning this. Unless Andre finds a 22-point word. I'm winning.
Please.
Oh.
Wait, I'm ready for clown.
Wait, no. Start timer.
Go clown.
Wait.
Actually,
I'm
start
looking for a
the
word.
timer. Start the timer.
Wait.
Good job. Oh my gosh, this is proof that you can beat an Andre.
You can. CAN. Chris. You can.
Guys, this is so rigged.
This is honestly such a bad game.
25. At least he's not losing. I mean, he's losing, but like,
How did you go 101? You were literally at like 90 something.
how did I win?
This is so not fair.
Shut up! You literally won like 2 games.
I win. I beat Andre.
He beat Andre.
Whatever. Oh god.
Yes, I first. Wait, what? I was
Okay. This is on, guys. Whoever wins this, I'll give them a moderator.